Okay guys, sorry, we're going to get interrupted by Mr. Gifford a couple of times. He's still doing afternoon announcements. But I've got a contractor coming over to my house to fix something, so I'm going to get a head start on this so I can get out and get over there. Okay, so we're going to do the 3 questions that you already did Part A for, but we're going to do Part B. We're going to use only energy formulas like you did in grade 11 to get the same answers that you got in Part A. Let's start with this first question, and remember, the very first thing you do in any energy conservation situation is you have to think about what types of energy you have. So if you were firing a cannonball off the ground, I mean, think about it as there's no height in the beginning. The cannonball just launches up into the air, so it would have speed, and if it has speed, it has kinetic energy. The cannonball is going to travel up into the air, it's going to go as high as possible, and just before it starts to fall back down again, it's actually going to come to a rest. And at that instant, it will have traveled its highest point. It will have no speed whatsoever, but it will definitely have height. It will have all gravitational energy. And in this question, that's it. So there's your transfer. So we always write a formula that says the total energy in the beginning has to equal the total energy at the end. This is a very easy situation because in the beginning there's only one form of energy, and at the end there's only one form. So the total energy in the beginning is all kinetic, and that must equal the total energy at the end, which is all gravitational. So as long as you understand this, what I just wrote on the page, that's actually the main gist of the question, because this is not memorizable. This expression will change for every question. So as long as you understand how the energies equate and work out, the rest is just details. You pull out your grade 11 formula sheet, you fill in the individual formulas. Kinetic energy was 1/2 mv squared, and gravitational energy, mgh. And as long as you have done the question correctly, you will have one unknown to solve for. And in this question, the unknown is how high does it go? So we are going to solve for h. Remember, in grade 11, usually if you looked at the equation, mass canceled out. So even though the mass of this question might be given, no, it's not. It's not given, and it's not going to be required because it cancels. Rearrange and solve for h, which maybe is something you didn't do last year. You might have just subbed numbers in. And although this does not look like what you had written down in Part A, if you examine it a little more carefully and look at it, you'll actually find that it is the same. So we've got our initial speed of 200 kilometers an hour, and of course that's got to be converted. Should have had that done before. That's 55.55 meters a second. You're going to square that, and you're going to divide by g. Now remember, g is never negative. The g value in formulas is always 9.8 meters per second squared. If you're subbing into an acceleration in a formula, you have to think about whether it's plus or negative. So when you did Part A of this question, you must have used negative 9.8 to get it all to work properly. But in the energy equation of this question, you're not subbing into variable A, you're subbing into variable g, and g is always positive. So you're not going to have any kind of a sign conflict with the top of the question. So square the top, multiply by half, and divide by 9.8, and you're done. You should have had a question. You should have had an answer of 157.5 or 0.47 meters. And that's done entirely with energy conservation and none of the 5 acceleration formulas. Now, I should mention at this point, the reason why we're doing this is because in grade 11 you kind of had a choice. You could do it one way or the other. But in the next couple of days, especially when you guys are back on Thursday and Friday, we're going to do energy conservation situations where you won't, there's no way to use the 5 acceleration formulas to get answers. You will have to use conservation of energy. So the bigger question here is, even though this might not have been your preferred way to solve a question in grade 11, this, unfortunately, but I want to say fortunately, is your future. You have to do energy conservation. So let's do a couple others here and get used to this even more. Okay, so this question where a guy is diving off a an upper height and belly flopping onto the person below is actually this question in reverse. So think about it like this. The person starts off here at rest. They're standing there, they're looking, they're ready to jump, they're not moving yet. That's all gravitational energy. Then they're going to fall, they're going to drop the full height, and just before they hit the person that's down there on the bottom, they're going to be traveling very fast with no height left. It's going to be all kinetic. So this question's actually the same situation in reverse, but that's okay. Total energy in the beginning is all gravitational. It has to equal the total energy at the bottom, which is going to be all kinetic. That right there is the most important part of the question, and the part that you have to get. Then you sub in your formulas, and that's not an important part of the question because formulas are on formula sheets, and the presumption is you're not going to do that part wrong. So sub in your formulas. You can cancel out mass if it occurs on both sides of the formula, but it's got to be in every term. Identify what you're trying to solve for. In this question, it's with what speed will he be traveling when he lands? So that's the V on the right-hand side of the formula. So isolate, and just take the half over and put it on the bottom. And while I'm at it, I might as well isolate the exponent that's on the V as well. And that'll become a square root sign across the whole left-hand side. So I'm running out a little bit of room here, but so G again is 9.8, never negative. Not that you would make it negative in this question anyway, because the guy speeds up as he falls. The height is given as 4 meters. Sorry, I missed my units in there, but I'm not going to add them now. This marker's too thick. And that should give you the answer for V. And I'll just quickly hammer it out here on the calculator beside the screen just to make sure. 9.8 times 4 divided by half, and then root of that answer gives you a final answer. You should have got 8.85 meters per second. So again, none of the acceleration formulas, just an energy expression. So the only time that this got any harder in grade 11 was the formulas weren't always so easy, left side, right side. So let's take a look at this question where the car is dropping off the cliff. Now if you read this question, I'm going to flip to a lined piece of paper for more room. If you read this question carefully, here's what it's describing, because you got to kind of understand this first. So it's describing that the car has dropped off the cliff and it's already in motion. So it's already fallen some distance when the question begins. So let's pretend the car's right there. It's already dropping with a speed of 12 kilometers an hour. So it's already got kinetic energy. It's also this high off the ground, which is height. And if it has height, it's got gravitational energy. So it's actually got two types of energy in the beginning. Now the car is obviously going to fall all the way down to the ground, but this question doesn't go all the way to the ground. Read the description one more time if that confuses you a little. It says, what will be the speed of the car when it's at a height of 10 meters? So let's say here, for example, it's going to fall further, but it still has more distance to go. And we're not going to look down there. So when the car is 10 meters off the ground, it's still got gravitational energy. And it's in motion still. So it still has kinetic energy. So that's a little confusing. The total energy before has to equal the total energy at the end of the question. And it's always total energy. You always add them all up. So here's a situation where mathematically it's going to look longer on the page, because in the beginning you've got two forms of energy added together. And at the end of the question, you've got two forms of energy added together. And this is a great example as to why in grade 11 I was trying to get you to start using little subsets in the lower right hand corner. Maybe things like an I for initial and an F for final. Because these variables aren't the same. And if you just leave them as e.g., ek, e.g., ek, technically you could argue that that would cancel left side, right side. They're not the same variable, and you want to indicate that somehow. And initial and final is usually the way most textbooks do it. So if that looks confusing, don't worry about it. You know the formula for each one of these energies, and if it just looks longer on the page when you sub everything in, who cares? It's just bed mass. A longer formula, as long as it's just bed mass, at this point in your education, you shouldn't even care. You shouldn't even think it's any harder. I don't think I have enough room across the page to write this out, so let me get another piece of paper and stick it underneath here like that. Okay, so let's write all these formulas. Gravitational energy is mgh. Kinetic energy is 1/2 mv squared. That equals the right-hand side of the formula. Gravitational energy is mgh. And kinetic energy is 1/2 mv squared. That's a lot of stuff, all in one line, and I don't want to get them all confused. So let me go back to what I just said and have these the I's and F's on here for the initial height, the initial speed, the final height, the final speed. Okay, so no matter how long the equation looks and how complicated it looks, there's only one unknown. And the unknown in this question is, what will be the speed of the car when it's at that final height 10 meters off the ground? That's this right here. So we're going to isolate for VF. The first thing I'm going to do is notice that there's a mass in every term. So let's get rid of that right away. And mass isn't given in the question anyway. Now, if it was grade 11, you'd probably substitute into all these variables. And I told you to do that in grade 11 because it was easier to keep track of what's what. Let's do that now. I'm not going to put any, stupid thing, stupid lights. I'm not going to put any units in because I want you to concentrate on the numbers going in the right spots here. So G is 9.8, HI is the initial height, and the initial height in the question is it's 30 meters off the ground. Okay, then there's a 1/2 mass canceled, so the initial speed is 12 kilometers an hour. Stupidly, I should have used numbers that didn't require any conversion here, but whatever. 12 divided by 3.6. It's 3.3 repeating meters per second, and that's going to be squared. So that's the left-hand side of the formula. The right-hand side of the formula, G occurs again, 9.8. The final height is 10 meters off the ground, plus 1/2 VF squared, and that's what we're solving for. Okay, so, and I'm only circling it because we're solving for it. You don't have to circle it. So you need to isolate and solve for VF. And you can take as many lines of work to do that as you want, but you know, you're kind of at the point now where you shouldn't need to put extra lines of work, and actually you should have rearranged before reaching this point. But let me hammer all this out. 9.8 multiplied by 30. I'm going to add on 1/2 multiplied by 3.3 repeating squared. I'm going to bring over 9.8 times 10. That's going to be negative. And my calculator already screwed up. Darn it, I have to start over again. 9.8 times 30. I'm going to add on 1/2 times 3.3 repeating. I'm still getting a problem. I need to reset my calculator. Sorry guys, this isn't what I want to happen on a video where I'm just wasting your time doing calculations, but let's do this one more time. Actually, you know what? I'm going to be I'm going to do what you really shouldn't do and put an extra line of work here. I'm going to do each one of these individually because I'm actually getting a problem with my calculator. I don't know why. One of the buttons is sticking, and that's messing everything up every time I do anything here. 5.55 repeating, 98, and 1/2 VF squared. I like to write 1/2 as 0.5. I don't know, I hate fractions. I try to get rid of fractions whenever I can. Okay, so that's a little bit better. 294 plus 5.5 repeating. Minus 98 when you bring it over. and divide by 0.5. Gives me 403.1 repeating, and that's actually still VF squared. So I got to take the root of that to get the final answer here. And sorry for the length of this solution, which is kind of needless. 20.07 meters per second, which hopefully is the answer you got in part A. And your answer in part A probably looks a heck of a lot easier. 3 easy givens, and you work out V2 and get 20.07. So if you remember from grade 11, doing it the energy way is not always the easiest, and certainly not always the shortest either. Sometimes using kinematics formulas was the easiest way to do it, but I'm telling you right now, we're going to be doing questions, like for example, we're going to be doing questions where you need to take the energy in a beam of red light as opposed to a beam of, say, blue light, because the energies will be different. And you're going to shine that light onto something, and we're going to have to conserve energy and create movement from the energy in the light. You will not be able to use kinematics formulas. Okay, so this is all for today. You actually don't need to do anything with this. I wanted to go through these 3 examples. We're going to continue tomorrow morning with a little bit more energy review, but we're going to take it one step further now. So we're going to start conservation of energy in grade 12 tomorrow morning, and probably spend that theme for most of the day. Okay, so have a good night, and I'll see you tomorrow morning in session 1.